For real numbers x, let p of x equal 1 plus cosine of x plus I sine of x minus cosine of 2x minus I sine of 2x plus cosine of 3x plus I sine of 3x, where I is equal to square root of negative 1. For how many values of x with 0 less than or equal to x less than 2 pi does p of x equal 0? Okay, so instead of just thinking about p of x as 7 different terms with x in it, we can instead what we can do is we can essentially pair up these two, pair up these two, and pair up these two. And what I'm gonna do is I'm gonna illustrate how you would plot each of these pairs in the complex plane. So this is the real axis, this is the imaginary axis, and I've just gone ahead and drawn the unit circle. So this would be 1, this would be I, and so on and so forth. What cosine of x plus I sine of x is equal to is, well, cosine of x plus I sine of x. This is actually defined as the point on the unit circle over, for example, over here, where this angle is equal to x radians. That's actually defined to be the point cosine of x plus I sine of x. And the reason is because if you try to take the magnitude of this, you get magnitude is square root of cosine squared of x plus sine squared of x, which is just equal to 1 by the Pythagorean identity of sines and cosines. So the magnitude is 1. And furthermore, what you're essentially doing is, well, if you have a right triangle, even in the unit circle in the real plane, you get that the x coordinate is cosine and the y coordinate is sine. So for all of these reasons, this point over here is cosine of x plus I sine of x. And for shorthand notation, we write it as CISX, cosine plus I sine of x. And what's really nice about this is we can also write this in exponential form, e to the power of I times x. Okay, so now that I've established that, we can go ahead and try the problem. Okay, so we're going to let cosine of x plus I sine of x, this thing over here, CISX, we're going to call this k. And what we can notice is that this is equal to k squared and this is equal to k cubed. And the reason is because CIS of 2x, which is essentially what this term is, this is equal to e to the I times 2x, which is e to the ix squared. That's k squared. And this term over here, cosine of 3x plus I sine of 3x, that's CIS of 3x, is equal to e to the I times 3x, which is equal to e to the ix cubed, which is equal to k cubed. So p of x is equal to k cubed minus k squared plus k plus 1. Okay, so how's that going to help us? Well, so what we can see is that p of x is equal to this thing. And you just want p of x to equal 0. So for how many x's is CIS of x a root of p of x? And that is what we're going to find out right now. So with a little inspection, you can see that p of x only has one real root. And you can think about it because if there is an imaginary root, we call this imaginary root z, then its conjugate, well, okay, so let's say z is equal to m plus nx. Then if z is a root, then by definition, its conjugate is also a root. M minus ni, excuse me, this is m plus ni. So if m plus ni is a root, m minus ni is also a root because p of x has all real coefficients. So there are either 2 or 0 imaginary roots. And if you just think about visualizing the graph of p of x, you see that when p of x is less than -1, then k cubed, k squared, and k are all negative, and it's easy to see that this sum is clearly less than -1. So below -1, there's a bunch of negative, and then p of -1 is equal to -2. And you can also see on the other side, if p of x is greater than 0, then either k cubed or k is going to be greater than k squared, which effectively means that when p of x is equal to 0, k is equal to 1, and above that, k is positive. And between -1 and 0, the graph would cross the x-axis one time. So this means that there are two imaginary roots. And so we can say the roots are z, conjugate of z, and a real number, where this real number is somewhere between -1 and 0. So we can say it's approximately -0.5, right? So the roots are z, conjugate of z, and r. Now the next thing we notice is that, hey, these three multiply up to -1. Z times z conjugate times r is going to be equal to -1 by Vieta's formulas. Which states that the product of the roots is -1 divided by 1. So z times the conjugate of z times r is equal to -1. However, since r is equal to -0.5, approximately, give or take, z times the conjugate z is going to be about 2. It doesn't really matter what it is. And we see that just as long as r is not equal to -1 or 0, because then z times the conjugate of z is not going to be equal to 1, and that's really important. And the reason is because back when I said that CIS of x always lies on the unit circle, this implies that the magnitude of k is equal to 1. However, since k is either 1 of z or the conjugate of z, because it can't be -0.5 or whatever r is, because r does not have magnitude 1. So k must be either z or conjugate of z. However, think about it. Z and the conjugate of z both have the same magnitude, because this magnitude is square root of m squared plus n squared. This magnitude is equal to square root of m squared plus n squared again, which means that z and z conjugate have the same magnitude. And a property of complex numbers is when you multiply them together, the magnitude of their product is the product of their magnitudes. So z times conjugate of z is going to be the magnitude of z times the magnitude of conjugate of z is going to be equal to the magnitude of z times the conjugate of z, which is going to be approximately 2, or just, you can say not equal to 1. So the magnitude of z squared is not equal to 1. So the magnitude of z is not equal to 1. But that's a direct contradiction, because the magnitude of k was equal to 1. And we saw that k was either equal to z or conjugate of z, which means that this is entirely impossible to have x with p of x equal to 0. I mean, excuse me, k with p of x equal to 0. So there are no x's, since magnitude of k is equal to 1, magnitude of z is not equal to 1, and k cannot be equal to z. So the answer is 0, and we're done. Thanks for watching, and I'll see you next time.